All right, welcome back. Hopefully this one won't be too terribly long. This is the one now, as we alluded to earlier in previous videos, where we're going to take a look at the actual frame rate tests. And I made a couple of videos to kind of simplify it. I took essentially a 1 second section of each, I recorded the emulator and took a 1 second chunk so that I lined up the top of the water tile that animates, and as soon as it moves down one frame, so we start wherever the top of the water tile is, and the next frame of the 1 second is when it first moves down, to animate. I tried to get it as close as possible to be all consistent that way, and then over the course of the 1 second, just basically frame rate, went frame at a time and counted how many water tile updates there were. So I've got 3 videos. The first video shows the original Ultima 4. Let me get that up here. So this shows the original Ultima 4 game. This is the actual game running, and I've measured it at about 5 frames per second. And this is my fully, if you want to say optimized, but it's only a 10-second clip, so I'll have to loop it. Hang on, let me do the loop thing. Yeah, loop, here we go. Okay, so this one is my the large memory intensive, 2.5 kilobyte unrolled loops, direct hard coded everything. All the positions are hard for the screen are hard coded, so that when it writes, it's just writing directly to hard coded spaces. And the only thing it's using the kind of indirect indexing for is to get the tile data, and when it makes the water loops, which is still pretty good, because even though the indirect Y, indirect comma Y, 0 page kind of indexing is, of course, very, very useful. There are a couple of other ways around that, somewhat. But when you're dealing with data that you don't know where it is, then, like, any given tile could be anywhere in the set. It's not a fixed position, whereas a screen memory is a fixed position. Technically, the water is too. I'm not even sure if I'm actually doing... When it comes to the water, technically I could be... let's see, where's the water animation? Yeah. Oops. Hey. Actually, I am doing absolute addressing here for the water animations. We're doing a loop, but we are doing... sorry, this is... let's close that for a moment. It's resetting when it... loops. So with the water animations, which I think I may have covered before, they're just simple, loops of, you loop from the beginning to the end, because we're moving the tiles down, so we start at the end. We're counting backwards. All of the loops, or most of the loops in here, I think all the loops in here, are using the method where you count down, and then you branch if it's not past 0. So as soon as it drops past 0 to FF, it triggers the flag. I forget which flag it is. I think it's a Z flag or negative flag. And then I think it's a negative flag. And then this doesn't trigger then, and it falls through. So we started. We're actually checking it on the Y, because for the animated tiles we are moving. There's 32 bytes. Let me get my other thing up here. We can see a little bit closer how this looks. Oops, that's not it. Here we go. So this is a breakdown of the tiles again, how they're laid out, the tile data in memory. 32 bytes, 15, essentially you can look at it as 15 rows of 2 bytes each. So row 15 represents 31, byte 31, and byte 30. And you go all the way up until you get to 0 and 1. So we started byte, but in this case, because the bottom row is actually being placed at the top, we pull those 2 bytes manually, and then at the end of each loop we put them in at the top manually, and those are now the water tiles are fixed. We know exactly where they are, so we can use absolute addressing on that for those. But anyway, so what we do is we start the loop at 29, because we want to take row 14 and move it down to row 15, which is the last row, and move all of them down from there. So eventually row 0 comes down to row 1, and then we put the last 2 bytes in at row 0. So that's how these all work. So this is pretty efficient in terms of cycling. You're only really not even losing, but this is a couple cycles, two or three cycles to check. Obviously each time, and of course your decrements and stuff. But the absolute addressing is pretty good in terms of memory or cycle count rather. I think they're 4 cycles, so they're a bit faster than if you use 0 page Y, which is upwards of 6 cycles. 5 to 6 at least, I think. Again, I'm kind of just going on memory here, but I know that it's better. Because I've already worked out how much better this addressing is, and even this addressing, it's the same, than using the 0 page method. So anyway, what we're going to take a look at today, though, that's for animating the water. So real quick, just to get back to our test. So that's what's happening here, is this is this screen. This is the game, well, not the game. This is the game. This is my my constructed thing. My graphics test and everything. What's happening here is we're drawing those 3 tiles as I just described. So there's 3 different water tiles. So we're doing 3 of those. And then we are fully redrawing the screen. There are no optimizations in the screen redraw to say, oh, this town has not moved. Don't redraw it. We're going to do that later. That'll be the next phase to do. So for right now, this is a full screen, top to bottom redraw of all tiles, every frame, and animating the water. And with the unrolled loops and the massive, like I showed before, where you pretty much hard code everything in, that is still, or is 15 frames a second. It's actually very quick. I was surprised how much that came out to be. So that is, of course, memory intensive, like you wouldn't believe. Like I said, it's 2.5K just for those routines, which are basically this. And I'm not going to go over this. I did this in the previous video, but basically, grab screen tile, load. We do the Y addressing to get the tile data, because in this case, we don't know what tile we're needing to draw. With the water, we can get away with hard code addressing because we know exactly where the water tiles are. They don't move. But in this case, any given tile could be anywhere in memory. So we need to do some kind of other addressing to get to it. So I just, for convenience, if there's a better way to do it, I could do it. But even using the Y method to get the tile data, we then place it in the hard-coded spot for this line. On this is line 8 on the screen, on the graphic screen. Whoops, that's not right. So we remember there are 8 lines for the border at the top. I've accounted for the borders with this particular method to duplicate what the game did in terms of where it goes on screen. So line 8 is our first tile, and you go line 9, 10, and you just hard code everything in using this method. And we basically do our various things. We basically use X to bounce back and forth between the 2 bytes, which are the, again, I'm only going to, which are these 2 bytes. So you can kind of look at this as, even though this is this represents the tile information essentially, this also could represent a screen position. Just obviously these addresses over here they wouldn't be sequential. But for any given pair of bytes, you have basically a left byte and a right byte, or whatever you want to call it, +1, +2, whichever way you want to look at it, or 0 +1 of the pair to put on screen. And that's what this does. This takes 1 byte, then it increments it, and it gets the next byte in the. So we get a byte, put it on screen. We increment both X and Y. In this case, now this is where it's going to be a little weird. In this case, we are drawing the tiles from top to bottom. So that's important, or at least interesting, when we get to the other bit. We are drawing the tile from this corner down to this corner when we draw it on screen with that method. So it's just all straight linear right all the way through. Now when we do the other method, which I'm about to show here, and I got to go over here because this has got the older version. This one now is the shorter method. This is the more traditional kind of method where you do loops and stuff, with a little bit of borrowing from what I did on the other side there to make it faster, I think. But this uses your more traditional kind of addressing, X with Y and everything, where the same thing with the tile. We get the tile that way, but then we store it on screen with an offset. And again, because this value, we construct the address. This address is put in into the 0 page when we figure out what tile we're getting. This one is constructed here from the table, essentially. But we're also doing some other tricks here. So the way this would really look is it would look like, because I've got 2 routines here that do the same thing, but they're almost identical, but they're slightly similar. So what we're doing here is we're getting the screen tile across the row. This is the X of that row. So if we're on row 0 of the first row of the tiles, and we're in like position 3, tile 3. That's what this would be. This would be tile 3. We multiply times 2. That gives us our offset across that row to use. We put it in X for indexing. We increment it once to account for the border, because when we get the screen table row data, where we actually get the tile row address from the table, then that's at the edge of the screen. So we got to add 1 to account for the border, and then we got to add 1 more to add to the end of the 2-byte pair, because in this case we're doing it, I think we're doing it backwards. Yeah, we're doing it backwards. Because we're running this loop, unlike the other loop, where I just said, hey, we go from top to bottom for the tile and down the screen. In this case, we're going up the screen. So we're starting at the end, almost like when we're doing the animation. We're starting at the last byte of the tile and the last byte of the row. That's why we need to get wherever the row... Yep, this is the row table start, which the start is actually going to be then the end of the tile. So row 15 of whatever, 8 plus 15 or whatever the offset, whatever the row on screen is. So we index in the table with the last row first, and we work our way up. So this is actually drawing all of the tiles backwards, essentially. It is going left to right when it draws the tiles, but it's going bottom to top per tile. So this method is a little messy because, again, I was using the Y indexing for both getting the tile and putting it on the screen, which means I have to preserve Y. I have to basically stick Y somewhere. I have to get Y for the screen position, and then I have to restore Y back in for the next tile, and then we decrement it for the next tile, and we do all this back and forth. So I felt that was a little messy, and it is. And also I thought maybe this could be improved a little bit in terms of speed, or at least in terms of coding, using a similar method of combining a couple methods. So what I came up with was this, where we basically get the table data, and I may be able to adjust this too. We'll see. But anyway, this works well enough. I think maybe. Oh no, we do it here. Yeah, we do it there too. Or yeah, we do it here too. So we get the low byte, and we add our X offset, low byte address, because remember, any given row of the screen starts. Well, I don't know if it really starts at a page boundary. Yeah, I think it does. Or at least it's within 40 bytes. I don't think any of the tiles, at least I guess it would probably screw up if it did, because I didn't actually think of that, because I just assumed that any given row of the screen addressing is going to start on some kind of boundary where you can go across, because as I understand it from everybody else's descriptions of how this works, is you can go across any given row. So like line, row, we call it row, but the line on the screen. So line 20 on the screen, right? Or any other line on the screen itself of the 192 lines, you can index across. If it crossed a boundary somewhere in the middle of the line, that wouldn't work. So they all have to line up on some kind of boundary where they don't cross a page boundary when you go across the line. And I believe that's well, it has to be true, otherwise this routine would not work. Anyway, so we clear the carry, we add it. So this right here is probably our biggest overhead, but I think the savings end up being worth it, and you'll see that they're slightly worth it. So now what we do is we do self-modifying code. And we're taking advantage of the fact that because we now know the actual address of the 2 bytes on screen that we're going to be putting, the high byte we can just stash because the high byte doesn't change. The low byte we add the offset, so not add 4, we add the X offset to it, which is up here. We do have to, by the way, when we do the second routine, we do have to rem this out, and I created basically a duplicate routine, so I did a jump around the old routine. But this, if you leave this in, will offset it by another byte, and then all the colors will come out wrong. It'll be in the wrong position on the screen. Anyway, that's just a little aside. So what we do is we take the low byte, and we stick it, because now we have a fake or not a placeholder. Well, it's a store instruction, but the address is just a dummy for right now. By the way, never, if you're going to use this method, never do this, because it will change this to a 0-page reference and nothing will work. Everything will be off. So make sure this is above 0 page when you're using this kind of faking up a dummy address that's just going to be changed dynamically later. Anyway, a little tip. I did that accidentally. I'm like, why is this not working? And, oh, yeah, duh. I looked in the actual memory of the computer. Or actually, I looked at the listing of the compiled listing, and I'm like, there were only two bytes here instead of 3. And I'm like, hey, what's going on? And oh, yeah, that's right. I put 00 in, and when it compiles, it uses this address when it compiles because we're changing it only when the program runs. And we do that. We create an address here and an address here right before the store statement. We add 1 byte to that to get to the low byte of each of these addresses. And then we get the high byte and just stash that at +2, which is these are reversed, but it's the high byte of that one. Now what we can do is we can load with Y, just like we normally do from the tile table, but we can just have a standard store statement, which saves at least a couple of cycles or a cycle or 2, but it does not need to use X then, which we can now, because X is being used, and I didn't say this before, X is our, I kind of did. X is our row to index into the table. So we really want to keep X, we don't want to swap X or do anything with X, because this is how we get the next row, whichever direction you're going or however you're doing it, into the table of the line addresses, the graphics line addresses. Now it becomes trivial, because now it's a straight store, just a standard store. We decrement Y to get the next tile byte. We get the next tile byte, and this one, which we've already pre-calced. Well, actually, we didn't. We did here. Sorry, I missed one thing. So when we put the low bytes in, we have to increment the second one, or the first one rather, because again we are doing this backwards. So we are doing it here to here to here to here. No. So we have to take the second. The first byte, because that'll be the first, because remember, we're going backwards through this tile data. We're starting at 31. So in 31, this needs to go to position 2, because this mimics the screen 2, has to go here. So we have to increment, once we store it, we increment the low byte of this address. And then we only have to store this one because it's already pointing to the correct address. And then it's just load, store, decrement Y, and because these addresses are now, we've done all the work up here, these addresses are now fixed to be this address and this address, respectively. This one goes here, and this one goes here. So now we've got a bit of a cycle savings, because we're saving at least a few cycles off of these store statements, even though we do have to calculate up here. But we don't have to do all of this stashing of the Y vector and getting it back. So there's a bit of improvement there. It is a little bit faster, but it's also much cleaner. It's also a little more elegant, though I'm not really going for that. I'm more concerned about performance. Performance versus memory, Obviously, this is very efficient because the actual draw loop is this, which is almost nothing. It's 50 bytes maybe or something like that. And even the overhead is only, there are 20 bytes or whatever it is. So that becomes really efficient for memory. Performance-wise, it's probably acceptable. I don't know if there's any way to really improve this more in terms of speed. I'll think about it. I came up with this one night just, trying to fall asleep, so maybe. But what we get is, then, we're going to show 2 more tests. The first test is going to show the full, longest memory, fastest method, combined with my first draw loop, the one that was the longer, more ungainly one here with all the swapping with the Y register. That's this one. No, I take that back. That's this one. So now we're looking at, and they're still this is still animating the water, doing a full screen redraw. And you can see it's quite a bit slower. It's dramatically slower. So this is where things get interesting as far as what do you want your game to do? If you were making something like this. Do you want your game to have this kind of performance on the left for animations, or this kind of performance on the right, but with 2.5K more memory, because this takes up a couple hundred bytes and this takes up 2.5K to do. But you can see the performance is dramatic. Now, between the two routines of my original, the one that I just broke down here, the original loop and the new loop, that is this one. And it is a slight difference. It's probably not terribly noticeable. I think the one on the right is a tad smoother, but it's not much. It is about a frame per second faster. So still worth doing, because you always want to optimize wherever you can. You never know. The thing about the optimizations and just the speed in general is, if you could save a handful of cycles, a couple of cycles, a cycle or two even. Remember, you have to draw all of these bytes have to get put to the screen. And to get the byte and to put the byte to the screen, it's 3,800, like 3,900 bytes or something like that you're touching, that you're getting and putting. So if you could save a cycle anywhere in one of those parts, in the get or the put, you're saving 3,000 or 4,000 cycles per screen redraw. And that's certainly going to improve performance. That's probably what's happening here. I'm probably saving about a cycle or two. But the advantage of it, or the thing you have to consider with that, and this is where all of these performance considerations come into mind, is compared to the real game. Now, compared to the real game, I'm only doing this. There's no background anything happening here. So, now granted, the original game, when it's just idling, is probably just it should only be doing this too. There's really nothing to check for the game except for the moon gates and the wind, because those do update even when you're idle. But that can't be a huge check or whatever. It's just random. I think the moon gates are on a cycle, so it's just a counter increase, until it hits a certain number of turns or whatever, or not even turns, but time-wise in the game. The winds are probably random. So there really shouldn't be. This or even the faster version should be what the Ultima games run. So this is what the Ultima games should run like in terms of performance when you're just sitting there, when there's nothing else on the screen or not too many other things to animate. Obviously, if you have a bunch of things on the screen being animated, that might be unique things. Like if you have like 4 monsters and water and the flags here. I haven't got the flags done. Those will be trivial, though. It'll have an impact. But for this type of a screen where you're just sitting there and there's some water to animate, or even just redrawing the screen, and that's all you're doing, which is what the game should be doing. Now, movement and all that stuff, obviously, but you never know where you're going to need time. So the more you can save, generally the better, because, yeah, you move, and now there's a whole bunch of stuff that gets checked, and some of that time of movement can be buried in the movement itself. You're not really paying attention to whether things are going 15 frames a second when you move. But if there's a noticeable lag, but anyway, that's that. This is about this kind of animation. So if you're doing like combat, right? Combat would be a good example. So when you have a combat screen up, there's going to be your 4, 6, 8 party members, right? And several monsters that all have to be updated with animations. Now, some of those are duplicated. The monsters is just you update the one monster, or maybe not. Maybe you pull a random frame. I don't know. It depends on how they do it. There's ways to do it. Otherwise, the monsters would animate all in sync. So you got to keep that in mind as well. That's probably why in some of the character sets, even in the main or whatever, there's like 4 monsters and there's 4 tiles of animation. Really, you only need one of those, and you could swap from another place in memory into the tile set. But they may not do it that way, because then, like I said, when you do that, all of the same monster, let's say orcs, would all, if they raise one hand, all of them would raise their hand at the same time. And if you have 4 different unique ones, and you pick one of the 4 to put them on the screen, when you animate them all or shift the data around, they all animate differently. So that's probably a good way to consider things. Anyway, these are the considerations you have. So this sort of animation, 15 frames a second is a maximum at this, but you have other considerations down the road. So if you're at 8 frames a second here, like this, and now you have 12 different monsters on screen to animate, or whatever it is, then it suddenly becomes a different thing. That animation goes, way down. So wherever you can save, to get to as fast as you can. So that's why this sort of thing may be a consideration, because it gives you extra. If this drops to 12, it's still going to look really good and really fast. On the other hand, animating the monsters is not a per frame thing. This is hammering. All of these are hammering as fast as they can. It's animate and display, animate, display, animate, display, one right after the other. There's no real pausing for anything, whereas when you're doing combat, not the except for water, the monsters are not animating every single frame. So yes, you're redrawing the screen, and you are animating the water. Let's say if there's water within the or thing or anything else like that, or some other torches or what have you, that are more of a every frame animation. But the monsters would be every 3 or 4 frames or something like that, or you could manage that, to mitigate some of the performance. Anyway, so those are some of the considerations, but I'm not really getting into that with this. I'm not really building the game here. I'm just mentioning it because if you use this as a base to build some kind of game, those are some of the considerations you want to have and why you want to try to optimize as much as possible, because you could run into other areas that you could use extra cycles for, and you don't want your frame rate to suffer too much. And then, let's see, I had something else I wanted to mention. Oh, no, that's... okay, so now... And then this is a backup. So this is the actual tile draw. I'm going to take a look and see if I can optimize things. Oh, the other thing was, we're also going to be looking at doing... yeah, okay. So what we're going to look to do next from here... Oh, actually, no, I gotta show... Wait, I gotta show one more thing. So what I did was, as I showed before, there is a map buffer, which, by the way, I moved to the top. Oh, here's another thing along with this. All of these tables that you use for anything like this, any kind of tabling, or your map data, this is the map data. This is a buffer. This is 1 kilobyte that basically is now built in, that will mimic, or could be used, as well. But right now, it's just the data in here just mimics as if you're on the map somewhere, and this is that map data for that area. This is actual map data from the map disks. So this is Lord British's castle area. I wanted to do this because I'm going to show you we can move around this little map, and eventually, if you wanted to, and I may do it, be able to load the sectors from the disk and place them in this buffer. But it is going to be, you always want to make sure all of these buffers sit at the top of a page. They got to be at 0 on the page, because you need that for indexing and calculations and other things, especially tables like this, where you're indexing with a single byte. So, this is like 6,000. This one I think is actually not on a page boundary, because it doesn't matter that much. It's within a page, because this is the map that gets drawn, so we construct this map from the bigger map, and then this is the buffer it uses to display that map onto the screen. So these are 121 bytes, and I had to pad them to get to 128. So these 2 buffers represent 256 bytes, 1 page. This map gets copied when you move to this map, and then this map will eventually be used as a comparison to this map to say, did that tile change and do we need to redraw it? And then this is on 6100, let's say, I think, and 6200, 6300, or whatever it is, right? Down the lines. 6400, 6500, and so, yeah, because I know this is 6600. So that's something you need to consider and make sure you do when you're doing any of these kind of tables that you need to index into in some way. So now, let me get my thing up here. So now, again, that's that map data. We are essentially right about here, or maybe here, somewhere around in there. Well, actually, maybe we're a little over than that. Because what I did was, as you notice here, I put 0, 1, 2, 3, 4, 5, 6, 7, 8, blah, 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 on the left-hand side, so I could figure out where the left-hand side was, and to make sure that as I was doing the calculations, I wasn't skewed, because it could be like, this line could be here, and then this line could start here, and then this line could start here. I could have been off. So I want to make sure I was off. So if you go here, you can see that's that data, just dummy data, so I can make sure visually that I'm lined up. So this is the movement through the buffer. When it hits the edge, it just doesn't go anywhere. Normally, you would replace that with get the next pair of sectors and reposition everything. And I'll probably, like I said, I would like to work on that, because then you could take your Britannia disk and stick it in, and you could actually wander around Britannia or the Underworld. So I think I might try that, because that's the next logical step for this sort of thing. It would be very basic, and it won't be optimized, because I'll just want to get it working, so it won't shift the buffer around, because these are made up of 4 sectors, 16 by 16. So 16 lines here. That's why I got it broken up here. 16 lines here, 32 wide, so halfway is 16, right? So this is one sector, this is the next sector. So this is like sector 5 and 6 of track I don't know, 16 or something, and then this would be track 17, 5, and 6. Luckily, the way the disc is laid out, it's very easy to figure out what they are. So the way I'm going to do it is I'm going to pull the sector in, and I'm just going to copy the sector into this place. But every time you move off the edge, it's going to get all 4 sectors. Normally, you would probably just shift the data and just get the 2 sectors you need, but in this case, I'm not going to mess around because that's a lot more complicated math and whatnot. So what we want to check here is I want to get a sense of speed for movement. So now, you can see that that's moving pretty good. It's got a decent amount of speed for... And again, this is still full screen, no optimizations. This is where the optimization of saying, hey, I've moved this way. Is the grass, is one of these tiles the same as it was before? So movement should be a bit quicker when I get that going. Animations will only go, the maximum animations could go, or the slowest they could go, I should say, is when the entire screen is, let's say, water, and every single tile has to be redrawn. Or drawn, you know. Because when the other optimization to do is, we'll go through here when you're idle, like this, and say, is this a tile? Is this a tile that needs to be animated? Is this an animated tile? No, no, no. It just skips them. And any animated tile, as I mentioned before, I was going to try to deal with that. Anyway, so this is the movement within the buffer, and I wanted to do this so that I could, you know, just take a look and see how speed-wise it worked in terms of, it was pretty fast. I like the way that this is moving. So even with the 8 frames per second animation of the water and the movement speed of a full screen redraw, this is a full screen redraw, mind you. I haven't done any of the other optimizations we just talked about. This is still moving around pretty darn good. So now there are other checks, obviously, when you move. This is checking for boundaries, but that's about it. So it's not checking to see if you get blocked. It's not checking to see, it's not handling monster generation or any other things in the game that there might be. That's the edge of the screen. So I think that's pretty darn good. So the next step is going to be the optimizations and seeing if we can get things to, like I said, be a little faster for the for screen redraw, and then seeing about maybe getting it so we can walk around the big maps. That's about it for now. I think that's. There's one other thing I want to do. I also want to. I just put in a note here. I'm going to do a. We're going to do a. I got to figure out the keyboard, you know, like V or something, and where we're going to switch between the fast redraw, the 15 frames per second redraw, and the one I just showed you, the 8 frames, the optimized smaller one, because I want to be able to compare any of these other optimizations I'm about to do in terms of updating animations or not, if not necessary, and updating the screen positions if they don't need to be done, and during movement. So I want to see the performance difference between those two, so I want to be able to flip it dynamically instead of having to recompile and kind of, you know, test that way. So that's next.